So last time we talked about the continuous case of a momentum operator. So our momentum operator in one dimension, for example, was minus I h bar d by dx. And we wanted to find what the eigenvalue of this thing was. And the eigenvalue equation is P acting on some function, on some vector, and giving us a number, the eigenvalue, times that same function back. Now, it's very convenient to label the eigenfunction by the eigenvalue. So let's do that. And this is, if I substitute this in here, this is a very simple first order differential equation that you all learned how to solve in your nursery school. So this is up to some constant, normalization constant, which is a convention. It's e to the power plus or minus. I think I prefer minus, although I wrote plus in the last lecture notes, px by h bar. Okay, so here the h bar is really here to make sure that we have the right dimensions, because here this has to be dimensionless, and p and x, they do have, p times x has a dimension of angular momentum, so you divide by h bar, makes it dimensionless. Right? So so this was the continuous case, and then so this also is these are also non-normalizable vectors. They're non-normalizable. Okay, what does it mean? So it means very easily, if you take psi of p and try to find its norm, you get a constant, an infinity, right? Because this guy is a phase factor. The phase factor from here will cancel the phase factor from here, and therefore you're integrating over the whole real line, and this doesn't converge. These are so there's a kind of a convention, and in some sense you can actually make them converge. And I'm not going to go into that, but if you have two of these guys and at different values of p, say one is p1, another one is at p2, then there is a sense in which you can say that this is actually given by a Dirac delta function of p1 minus p2. When p1 is equals to p2, of course it's infinity, as we saw here, but it's infinite in a particular way. And when they're not equal to each other, you can show that that's zero. That's pretty easy to show. Okay, so this is called an orthonormality condition. And what it is, condition, what it is doing, it is generalizing the case for the finite dimension. In the finite dimensional case, if I take this and this, these are my bases for the two-dimensional case, and let I be one of these vectors, okay? So I be one of these guys, then I or j, and then what we can show is very easily that if I take the inner product with I times j, you get nothing but the Kronecker delta ij, right? And what this is doing, this is generalizing that to the continuous case. I'm assuming that all of you have seen the Dirac delta function. So the Dirac delta function, if you haven't seen it, it's not really a function, it's a distribution. It's like that poem from Sukumar Rai, which begins with Dash Guru Guru Noy Ashulete Pakishe. So although this is called a guru, but it's not actually a guru, it's a distribution. So any which goes infinite, that's when it's its argument is 0. So this goes infinitely high. So I'm not good at drawing infinite things. Infinitely high and infinitely thin, but in a way such that the area under it is 1. So minus infinity to plus infinity, delta of x, d of x is defined to be 1. And there are many ways of defining such a function. And one is the top hat function, where you take a top hat and, which has a, sorry, this is not a very good top hat. And so, its height is 1 over epsilon, and the width of the top hat is epsilon. So the area over here is 1. And then what you do is that you take epsilon to 0 from the positive side, so that the top hat gets thinner and taller in a way such that the area under the curve remains the same. So that's one way of defining this is called a representation of the Dirac delta function. Okay, so okay, what do I have next? Okay, so P is actually, we saw that these, in the discrete case, SZ, SX, and SY, these matrices, they were Hermitian matrices, right? So in the case of continuous, case, how is that P is, say, a Hermitian operator, right? So Hermitian, or in the continuous case, this is called a self-adjoint operator. The two are almost the same, but not quite the same. So this is a self-adjoint or a Hermitian operator. Okay, so what is a self-adjoint operator? Before we can define what a self-adjoint operator is, we have to define what an adjoint is. So let O be an operator. Then its adjoint is, so the adjoint of an operator is defined by its action on vectors or on functions. So if O is acting, say, on some state psi, it gives me another state, and let me write that state like that. And suppose I take the inner product with any arbitrary state. So in this definition, the state phi and psi are arbitrary. Okay, O is not, but these two guys are arbitrary. So this is, if I take the complex conjugate of this number, then I could get this number by some other operator. Let me call it O dagger, which will act on phi, this guy, and give me some state. And if I take the inner product with psi, okay? So this operator, which acting on phi and then sandwiched with psi, gives me this thing. This operates for any psi and phi. So this is for all phi and psi. And by the way, the notation here is that O hat acting on psi is what I'm defining, O of psi. So this is the adjoint. This is an adjoint operator. So a self-adjoint operator, or a Hermitian operator, a self-adjoint operator is, okay, somebody, I didn't understand the integration of psi star, something, infinity, and then again, page P1, P2. Okay, I'll come back to that in a second, okay. So a self-adjoint operator is when this thing, that is this thing, which let me write is phi o hat psi star is equal to so basically this thing is equal to itself but without the dagger here. So that means it'll be over here it'll be psi o phi. Okay, so this is the definition of an adjoint operator. Should be add here. Okay, so this is what we mean by O is equal to O dagger. Okay, because this thing is equal to this thing except the dagger. So now we ask the question, is P self-adjoint?
Sir, the O, is that any operator or some certain operator?
Self-adjoint operator.
Oh,
A self-adjoint operator will satisfy this for any psi and phi. Okay?
Okay.
So that's the idea, is that not all operators will be self-adjoint, but operators which satisfy this is going to be self-adjoint. Now the question is P, is P self-adjoint? And let's see. So if I take some state and apply P on it, sorry, here I'm switching up the psi and phi, then what does this mean? This means that I'm integrating from minus infinity to plus infinity. World War III veteran, you probably want to look at this. So I'm taking this psi star, and then there's X. What is P? The P is a representation of H bar by I. Just give me 1 second. I have a very restless dog at home, and he wanted to go to the balcony. Anyway, so H by I, and then D by dx acting on phi. And then the whole thing is integrated, okay? So now what we do is that...
Sir,
yeah?
Why is it H bar over I?
Oh, this is, I defined it as minus I H bar, right? So this is H bar over I.
Oh, I see.
Yeah. Yeah, sorry about that. Yeah, it's just like, so sometimes I don't like to write the minus sign, so I just push the I downstairs. So here what we do is that we do an integration by parts. So if I do an integration by parts, then what I have is that minus infinity to plus infinity, and then H by I, this is a constant, so it doesn't matter. So there's and inside the derivative, there is psi star of x, phi of x. And the whole thing is integrated. And then we have the other term, which is minus from minus infinity to plus infinity, H bar by I. I could have just pulled it out of the integral. And the derivative operator is now acting on psi star of x. And then phi of x is just there. Now, here comes the part where its self-adjoint, is different from permission. So what is happening here is that this is a total derivative, right? This is a total derivative. So I can do the integral very easily. So the integral is nothing but H by I, and then psi star of x, phi of x, evaluated at plus infinity minus infinity. And then we have this thing where it is plus or it doesn't matter what. Sorry, let me just keep to the convention. H by I minus infinity to plus infinity, then phi of x, and then actually I'm going to put this inside in the following way. I'm going to put a plus sign here, and here I'm going to put a minus h by I d by dx phi. Okay. Now here we have to evaluate these functions at plus infinity and minus infinity. But these are functions which are square integrable. I didn't really introduce this term before, but I introduced the idea. Because they're part of a Hilbert space, that means that these things, when you integrate them, they converge. The integral converges. What it means that this must go to 0 rapidly enough as x goes to infinity, right? Otherwise, of course, this integral would not converge. And because this is a boundary condition that at spatial infinity it's 0, we see that this term is 0. And this is the condition that we have to apply for the infinite dimensional case, which was not there for the finite dimensional case. For the finite dimensional case, we didn't have to think of our vector having some boundary value. And that's why its self-adjoint is a more general condition than Hermitian condition. Anyway, so that is 0. And because that is 0, we are left with just this guy. But what is this guy? Let me just zoom out a little bit. This guy is nothing but, if I take the conjugate, complex conjugate, then this is going to be h by I d by d of x acting on psi, and the whole thing complex conjugated times phi of x, d of x. But this is nothing but p acting on psi, inner product with phi, and the whole thing starred. Okay. And this, if you go back, is the left-hand side. What was the right-hand side? The right-hand side was this thing, psi p of phi, and this is precisely the definition of a self-adjoint operator. And therefore, we see that P is a self-adjoint operator.